Greetings, students. Welcome to Screencast number 2. This one's about scientific notation, something we began learning about in class. Alright, so it works the same way as the last one. I present to you very real-world problems in which we solve them using the techniques learned in class, and then I present to you a different problem in which you use similar techniques to find the solution and report back to me your findings in one way or another. Alright, I enjoyed the first one. Hope you did too. Here comes the second one. This one is about more particle physics, or your problem will be. But the first one we're going to start off with has to do with astronomy. It says scientists have discovered over 100 exoplanets. These are planets outside of our solar system. Interesting. One of these exoplanets orbits the star Epsilon Eridani. Which is right here, as you can see in the diagram. The mass of this exoplanet is about 2.3 times 10 to the 27th power kilograms. The star and the exoplanet are about 10.5 light years from the sun. That, as you know, is very far away. The question is, and there are two of them, how many times more massive is the exoplanet than Earth? Which of course implies that this exoplanet, this other planet, is much larger than Earth, because Earth has a mass of 6 times 10 to the 24th kilograms. As you can see, the exoplanet is 2.3 times 10 to the 27th kilograms. You already know it's bigger. Forget the 6 and the 2.3, okay? Look at the exponents. Earth's exponent is 24. This new exoplanet's is 27, thus instantly making it larger because 10 to the 27th, of course, is larger than 10 to the 24th. We know this. One has 27 zeros, the other has 24. So it's already bigger. The question is, how many times more massive? In other words, how many times bigger? And then we have to answer the question, given that 1 light year is equal to 9.5 times 10 to the 12th kilometers, wow, that is really, really fast. What is the distance in kilometers from the sun to the exoplanet? Okay, so we're going to solve both questions, and then I'll present to you your question, which has to do with particle physics. First and foremost, let's do the first question. How many times more massive is the exoplanet than Earth, which has a mass of 6 times 10 to the 24th kilograms? In order to find how much larger something is from another, you don't subtract, you divide. That's right. We want to know how many times greater is the exoplanet than Earth, which means the exoplanet needs to be in our numerator, its mass, which means the Earth, its mass, will be in the denominator because basically we're dividing. So let's do that. The exoplanet's mass is 2.3 times 10 to the 27th kilograms, and Earth's mass is only 6 times 10 to the 24th power kilograms. All right, so we need to divide this. All right, so let's do that. Remember, whenever you're dividing numbers in scientific notation, think of it in terms of parts. There is no need to look at it all as its whole. We have the left part, which is 2.3 divided by 6, which is 0.383 repeating. Feel free to confirm that using a calculator if you wish. And then we have to take the 10 to the 27th times 10 to the 24th. Well, we remember from the quotient rule of exponents that you subtract the exponents when you're dividing them. So this is 10 to the, 27 minus 24 is only 3. However, we're not done here. We are not done. Remember, this is the exoplanet's mass, and this is Earth's mass. Why are we not done? Because remember, true scientific notation, make sure that this constant, this first number, is between 1 and 10, but not including 10 itself. Okay? So it can be 1, and it can go all the way up to 9.9 repeating, but it can't be 10. So, as we can see, 0.383 repeating is less than 1. So we have to move the decimal right here to the right 1 unit, so it ends up right there, because 3.83 repeating is between 1 and 10. So we'll rewrite this as 3.83 repeating times 10 to the, okay, now we remember we have to change the exponent. We cannot keep this exponent as 3 because we shifted the decimal one place to the right. And remember the rule that we said. If the number gets bigger, as it did right here, 0.383 repeating became 3.83. repeating, which means it did get bigger. If the number gets bigger, this exponent must get smaller. And because we moved it one place to the right, this 3 must go down by only 1. So now it's squared. So how many times bigger is the exoplanet than Earth? Well, it's 3.83 repeating times 10 to the second power, times more massive than Earth. Okay, now really what is that? Well, if we wanted to approximate this, this is about 383 times more massive than Earth. So that is quite large, as you can see. All right, so we solved the first problem, and the first problem was how many times more massive is the exoplanet than Earth. Now the second problem, as you can see here, is given that 1 light year is equal to 9.5 times 10 to the 12th kilometers, what is the distance in kilometers from the Sun to the exoplanet? The second question is, given that 1 light year is equal to 9.5 times 10 to the 12 kilometers, what is the distance in kilometers from the Sun to the exoplanet? Well, we need to know how many light years it is. And look, right here we have it. The star and the exoplanet are about 10.5 light years from the Sun. All right, good to know. So let's write that, 10.5 light years from the Sun. Now here's what we also know. We know that 1 light year is 9.5 times 10 to the 12th power in kilometers. That is crucial information for us to know, simply because if we know 1 light year is equal to this, we need to know how many kilometers 10.5 light years is. So we take 10.5 and multiply it by 9.5 times 10 to the 12th. Now think about what that means. The reason this makes sense is, think about it. If 1 light year is this, then 2 light years would be this times 2. And 3 light years would be 9.5 times 10 to the 12th times 3. And 4 light years would be 9.5 times 10 to the 12th times 4. But we don't want 1, 2, 3, or 4 light years. We want 10.5 light years. That's why we're multiplying. So since 1 light year is this, 10.5 light years would be whatever this product is going to be. Now notice the way I wrote it. As you can see, we want to keep this in scientific notation. So what we can do is kind of group together, quote unquote, like pieces. The reason for that is this is in scientific notation. And so therefore, let's multiply the constants together first. 10.5 times 9.5 is going to give us 99.75. And then because there's nothing to multiply this 10 to the 12th power by, you simply, as you know, carry it down. Very nice. Are we done though? No, because we need it in scientific notation. Which means 99.75, way too big because it has to be between 1 and 10, not including 10. So we got to take this little decimal right here and we got to move it to the left. So let's do just that. And as we move it to the left, this becomes 9.975 times 10 to the, but keep something in mind. This time, 99.75 became smaller. So therefore, this exponent 12 must get larger by 1. So it's times 10 to the 13th, and of course, kilometers. So here is our answer. The distance in kilometers from the Sun to this exoplanet is 9.975 times 10 to the 13th kilometers. That is a very, very massive distance, as you can imagine. All right, very good. So we solved both problems, which means it is now time for you to use very similar techniques to solve this problem. Your problem to solve has to do with this. E equals mc squared, also known as Einstein's mass energy equivalence formula. Very famous. I know you have heard of it. But have you ever used it before? If not, you're in luck. Today you're going to, okay? In fact, you're going to use this very famous formula to calculate a very important number. Now, if you want to, feel free to go on the internet and you could read more about it. It was the formula that gave birth to the atomic bomb, all right? It was for the first time, and I'm reading right here, the first time connected the mass of an object with its energy and heralded a new world of physics. So when you get a chance, feel free to Google E equals mc squared. You're more than welcome to look it up. It's got a lot of information. Very famous equation. Very, very famous equation. There's a lot to read about it if you'd like on many different websites. I just found this one on The Guardian. What are you going to do with it, though? Well, as you can see, it is very, very famous. I mean, look. Now that's dedication to science. That guy not only tattooed E equals mc squared on his arms, look what he also did. F equals ma, do you know that one? Force equals mass times acceleration. Equally important, just as famous. And then look at this. I mean, this is a statue. That's in Germany. A statue of that very famous formula. All right, so how are we going to use it? Well, here's your problem. The energy corresponding to the mass of an electron is given by the equation E equals mc squared. That's why it's called a mass-energy equivalence. In this equation, c is the speed of light, 3.00, or just 3, of course, times 10 to the 8th meters per second. Again, extremely fast. And the mass m of an electron is 9.11 times 10 to the negative 31st kilograms. Okay, that is so amazingly small. Calculate the energy corresponding to the mass of one electron. Okay, so you're going to use a formula just like you've used all formulas in your life. Only this one just has pretty much nothing but variables except for, of course, the exponent that is squared. So you know how to use that, though. Now, with any formula, it helps to kind of define your variables according to the problem. We are going to calculate E because we need to calculate the energy corresponding. Well, that's E, which means we need M and we need C to insert into that equation. Well, do we know M? Absolutely. M is the mass of an electron, which is 9.11 times 10 to the negative 31st power. And we also need to know C if we're going to use this equation effectively. Let's see here. Does it give us C somewhere in here? Aha! C is the speed of light. As we said, 3.00 times 10 to the 8th power. So I'm just going to write 3 times 10 to the 8th. Now, what is your task? You're going to take this and you're going to send it into that variable. You're going to take this and you're going to send it into that variable. And you're going to make a nice, interesting looking equation that you need to simplify. You need to actually figure out what the math is behind the multiplication that you are doing. State your answer in true scientific notation, and you will have found exactly what the problem is stating. The energy corresponding to the mass of one electron. And congratulations, you have effectively used E equals mc squared, quite possibly the most famous formula that has ever been written. Very, very important. And side note, by the way, if I ever became a DJ, that would be my DJ name, MC squared. Get it? Yeah, I'm funny. All right, you're all probably looking at your screen right now saying, no, Mr. Ripes, you are not. Okay, well, maybe you're right. Anyways, please respond to this screencast with your answer in any way, shape, or form. That could be a screencast of your own. That could be a written response or typed response, as long as you're explaining your work. It could be a video of your own. It could be an audio recording of just your voice. And I'm still waiting on someone to make a Vine of these things in their response. That would be cool if you can explain this in 6 seconds or less. Now, of course, you're not limited to those. If you can think of another creative way to tell me the information and how you got your answer, I'd be more than happy to hear it. Anyways, that's it. Feel free to email me if you have any questions, and good luck.